There is a number that sounds modest until you actually sit with it. The sun releases roughly 3.83 times 10 to the 26th watts of energy every single second in every direction forever. Almost none of it is used. Almost all of it simply leaves, unclaimed, into the dark. In 1960, a physicist proposed something that sounds like science fiction, but was published as serious astrophysics, that an advanced civilization, growing the way civilizations grow, would eventually need more energy than any planet could give it, and would be forced to build something around its own star to catch what was otherwise being wasted. But here is the part most people get wrong. The popular image, a solid ball wrapped around a sun, is not what was proposed, and it is not what the physics allows. What was proposed is stranger, more fragile, and far more revealing about the limits of any civilization, including our own. If you enjoy deep space and science content, do me a small favor, hit that like button and subscribe. It genuinely helps this channel grow, and there is much more like this coming. Get yourself comfortable. Let's begin. The idea did not arrive wrapped in spectacle. It arrived on a single page in a scientific journal, written in the dry, careful language of a working physicist thinking out loud. In 1960, Freeman Dyson published a short paper in the journal Science under a title that gives away nothing of what it would eventually become in the public imagination. He called it Search for Artificial Stellar Sources of Infrared Radiation. Not a manifesto, not a blueprint, a search proposal addressed to other astronomers, suggesting where they might look if they wanted to find evidence of intelligence elsewhere in the galaxy. Dyson's reasoning followed a simple chain, the kind of chain that feels almost obvious once it is laid out, and almost invisible until someone lays it out for you. Civilizations, if they survive long enough and continue developing technology, tend to use more energy over time, not less. A society that masters fire eventually masters coals. A society that masters coal eventually masters oil, then the atom, then whatever comes after the atom. There is no natural ceiling to this progression built into the chemistry of wood or the physics of uranium. The ceiling, if one exists, comes from somewhere else entirely. It comes from how much energy a planet's star happens to produce, and how much of that energy a civilization has figured out how to capture. For nearly all of human history, the answer has been almost none. The portion of the sun's output that reaches Earth and is actually converted into usable energy by anything humans have built is a fraction so small it barely registers against the total. Dyson's insight was not about us. It was about what comes after us, if anything does. He reasoned that a civilization with enough time and enough technological continuity would eventually run out of planetary sources and be forced to look outward, toward the star itself, as the only energy supply large enough to keep feeding an appetite that never stops growing. This is where the popular image starts to drift away from what Dyson actually wrote. Most people picture a solid shell, a continuous surface wrapped around a star like a ball around a marble, sealing it off entirely from the outside universe. Dyson himself never used the word sphere. He used the word shell, and even then, he was careful to describe something closer to a swarm. Not one continuous surface, but a vast number of separate structures, orbiting independently, each one small compared to the star, each one doing its own quiet work of catching and using a portion of the light that would otherwise pass by unclaimed. The science fiction version, solid and seamless, came later, built by writers who found the swarm less satisfying to imagine than a single, complete enclosure. The physics, as it turns out, agrees with Dyson and not with the writers, for reasons we are about to spend considerable time on. There was also a second half to Dyson's proposal, and it is the half that gives the paper its actual title. If a civilization did build something like this, it would not vanish without a trace. Energy cannot simply disappear once it has been used. The basic physics of thermodynamics demands that any structure absorbing starlight and converting it into useful work must eventually release the leftover heat back into space, and it can only do this as infrared radiation, the same wavelength your own body radiates as warmth into a cold room. Dyson proposed that astronomers searching for extraterrestrial intelligence should stop looking only for radio signals, the method proposed the year before by physicists Giuseppe Cocconi and Philip Morrison, and start looking for stars that gave off far more infrared light than their size and temperature could otherwise explain. A star behaving strangely in the infrared, in other words, might not be a strange star at all. It might be an ordinary star with something built around it. That single idea, half engineering thought experiment and half search strategy, is the seed of everything that follows. Dyson did the arithmetic on what a civilization's energy appetite might eventually demand. What he did not spend much time on in that one short page was just how staggering the supply side of that arithmetic actually is. To understand why no one has built one of these, and why the absence of one tells us something real rather than nothing at all, we have to look first at exactly how much energy is sitting there, in the middle of our own solar system, waiting. It helps to remember what kind of moment Dyson was writing in. The year was 1960. Infrared astronomy itself was still a young field, barely capable of the kind of large-scale sky survey that a search like this would eventually require. The first dedicated search for radio signals from other civilizations, Project Ozma, had only just begun the year before, aimed at two nearby stars by the astronomer Frank Drake. The idea that intelligent life elsewhere might be detectable at all, by any method, was itself a fringe proposition inside mainstream astronomy. Dyson's paper was not trying to describe a civilization like ours. It was trying to describe what any civilization anywhere would eventually be pushed toward, simply by following the logic of growth far enough into the future. He was reasoning about a destination, not drawing up plans for how to get there. That distinction matters more than it sounds like it should. A thought experiment about where physics and growth eventually lead is not the same thing as an engineering proposal. Dyson never claimed anyone could build what he described. Not soon, not easily, not even within a single civilization's working lifetime. He was reasoning backward from a simple physical fact. If a civilization keeps growing its energy, used the way every human civilization on record has done, century after century, decade after decade, technology after technology, then there comes a point where the only remaining source large enough to satisfy that appetite is the star itself. Everything else, every fuel, every reactor, every fusion concept on the table, is a rounding error next to what a single star produces every second without trying. To understand why a star becomes the only adequate answer, it helps to sit for a moment with the actual number. The Sun's total power output, calculated from its surface temperature and size using a piece of physics called the Stefan-Boltzmann law, comes to approximately 3.83 times 10 to the 26th watts. Written out in full, that is 383 followed by 24 more zeros. Numbers at that scale stop meaning anything on their own. They need to be brought down to something a human mind can actually hold. Consider it this way. All of human civilization, every car, every factory, every server farm, every light left on in every empty room, consumes energy at a rate of roughly 18.5 terawatts. Over a full year, that adds up to something in the neighborhood of 600 exajoules. It sounds enormous, and in human terms, it is. Now place that figure next to the sun. The sun produces an amount of energy equivalent to humanity's entire annual consumption in a fraction of a second, a span of time too short to register as anything at all to a person standing in a room. By the time you finished reading that previous sentence aloud, the sun had already released more energy than every power plant, every reactor, and every dam on Earth would generate in a year, several times over. In simple terms, the sun is not just bigger than our energy problem. It exists in a category that makes the word bigger almost meaningless. This is the gap Dyson was reasoning about. A civilization capable of building anything at planetary scale would eventually find itself in a strange position, surrounded by more usable energy than it could imagine spending, sitting unclaimed 93 million miles away, arriving every day as light that mostly passes by a planet and continues on into the dark. There is a deeper piece of physics buried inside this idea, one that a researcher named Jason Wright would return to decades after Dyson's original paper. It concerns a concept called the Landsberg limit, a thermodynamic boundary on how efficiently any structure, anywhere, built by any civilization, could ever convert starlight into usable work. No engine, however advanced, captures energy with perfect efficiency. Some fraction is always lost, and that lost fraction has to go somewhere. It cannot be destroyed, only converted into a less useful form, and the form it converts into is heat, radiated back outward as infrared light. This is not a limitation of human engineering. It is a constraint built into the laws of thermodynamics themselves. The same laws that explain why your body, sitting quietly in a room, is still radiating warmth you cannot consciously feel yourself losing. What this means in practice is that Dyson's original detection method was not a guess dressed up as science. It followed directly from physics that can't be avoided. Any structure large enough to capture a meaningful share of a star's output would necessarily glow in the infrared, whether its builders wanted it to or not. The waste heat is not a design flaw to be engineered away. It is a signature baked into the act of using starlight at all, regardless of how advanced the civilization doing the using might be. Consider what this means for scale. A swarm of collectors capturing even a modest fraction of the sun's total output. Something on the order of 3 times 10 to the 24th watts, less than 1% of what the sun actually produces, would still represent an energy supply roughly 160,000 times larger than everything human civilization currently uses combined. That is not a stepping stone towards some larger goal. That is, by itself, enough energy to dwarf every industrial achievement in human history compounded together, and it would still be leaving more than 99% of the sun's output completely untouched, pouring outward into space exactly as it does today. The energy, in other words, is not the problem. It never has been. The sun produces more than enough, more than any civilization at any plausible stage of development could meaningfully exhaust. The problem, the one that has occupied physicists and engineers for over 60 years since Dyson's paper, is what you would actually have to build, out of what materials, to catch even a sliver of it. And that is where the numbers stop being merely large and start becoming genuinely punishing. We have established that the supply is, for all practical purposes, infinite. What we have not yet asked is whether there is enough matter anywhere nearby to build something capable of using it. It is worth pausing here, before the numbers grow heavier, to picture the moment when this idea first reached people outside of physics journals. Dyson's paper did not arrive with fanfare. It sat quietly in the pages of Science, read mostly by other astronomers, for years before the broader public encountered anything like it. The phrase Dyson sphere did not even originate with Dyson. It was coined later by writers and popularizers trying to give his idea a memorable shape. And in doing so, they reached for the version that was easier to picture, a solid ball rather than the version Dyson had actually described, a loose and scattered swarm. By the time the concept filtered into science fiction throughout the 1970s and 80s, the swarm had all but vanished from the popular imagination, replaced by gleaming, continuous shells in novels and later in television and film. The image stuck. The physics, quietly, did not agree with it. That gap between the popular image and the original proposal is not a small detail. It shapes almost everything that follows in this story. When people ask why no one has built a Dyson sphere, they are very often picturing the wrong structure entirely, the solid shell rather than the swarm, and asking a question about an object that the physics rules out almost immediately, for reasons we will get to shortly. Dyson's actual proposal, the swarm of independent collectors, survives that objection. It is the version that remains, even now, a live and serious subject of study among physicists working on what are sometimes called techno-signatures, the observable fingerprints that an advanced civilization's technology might leave behind. Return for a moment to the energy itself, because the scale deserves one more pass from a different angle. Imagine every nuclear power plant on Earth, every coal plant, every hydroelectric dam, every wind turbine and solar panel, all operating simultaneously, all of their output combined into a single number. That combined number describes humanity's entire technological civilization at full capacity. Now imagine holding that number next to the sun's output for a single heartbeat, not a year, not a day, one heartbeat, roughly 1 second. In that single second, the sun releases an amount of energy that exceeds humanity's entire annual output by a factor in the tens of thousands. To put it in human terms, the sun does in under a second what it would take all of human civilization, running at full capacity, more than 10,000 years to accomplish. This is the gap that gives the entire concept its gravity. A civilization that managed to capture even a vanishingly thin slice of that output would not be solving an energy crisis. It would be stepping into an entirely different category of existence, one where energy scarcity, the force that has shaped nearly every war, every migration, every economic system in recorded human history, simply ceases to apply in any recognizable way. Dyson understood this. It is why he framed the structure not as an engineering milestone, but as a marker of civilizational maturity, a sign that a species had crossed some threshold beyond which planetary resources could no longer contain its needs. And yet here is the quiet, sobering turn this section has been building toward. None of this energy abundance answers the question of how to actually catch it. The light is there. It has always been there, arriving every day, mostly unclaimed, indifferent to whether anyone below is ready to use it. The Landsberg limit tells us that no structure, however advanced, will ever capture that light with perfect efficiency, and that some of it will always return to space as waste heat. the very signature Dyson proposed astronomers search for. But before efficiency becomes a meaningful concern, before anyone can worry about thermodynamic limits on conversion, there is a more basic question waiting underneath all of it. What exactly would you build the collector out of? And how much of it would you need? Think of it the way an engineer might think about a much smaller, much more familiar problem. A solar panel on a rooftop does not generate electricity out of nothing. It requires silicon, wiring, a frame, glass, and a surface area large enough to intercept a meaningful amount of sunlight. Scale that same basic requirement up by a factor large enough to intercept a percentage of an entire star's output, and the surface area required stops being measured in rooftops or fields or even continents. It begins to be measured in units that only make sense at the scale of planets. A swarm of collectors capable of meaningfully using even 1% of the sun's output would need a combined surface area many times larger than the total surface area of every planet, moon, and asteroid in the solar system added together. That is not a difficult construction project. That is a project that consumes entire worlds as raw material, and even then, only partially. This is the moment where the conversation has to shift, because energy was never the constraint. Matter is. The sun will keep producing 3.83 times 10 to the 26th watts, whether or not anyone ever builds anything to use it. In the same quiet, indifferent way, it has been producing that output for roughly 4.5 billion years already, and will likely continue producing it for several billion more. The bottleneck has never been on the supply side of this equation. It has always been on the construction side, in the solid, physical, unglamorous question of where the raw material for a structure at planetary scale is actually supposed to come from, and whether there is enough of it anywhere within reach to make the idea anything more than an exercise on paper. Start with what is actually available. Add together every rocky planet in the solar system. Mercury, Venus, Earth, Mars, along with the Moon and every asteroid in the main belt. And the combined mass comes to somewhere in the neighborhood of 1.2 times 10 to the 25th kilograms. That number, on its own, sounds enormous, the kind of figure that should be more than enough for anything. It is not. Not for this. Consider the asteroid belt specifically, because it is often imagined as a vast, inexhaustible quarry of raw material, scattered across the gap between Mars and Jupiter, waiting to be mined. The reality is considerably smaller. The total mass of everything in the main asteroid belt, every chunk of rock and metal between those two orbits, comes to approximately 2.39 times 10 to the 21st kilograms. To put that in human terms, the four largest objects in the belt, the dwarf planet Ceres, along with the asteroids Vesta, Pallas, and Hygeia, together account for well over half of that total mass on their own. The rest of the belt, the thousands of smaller bodies that show up so dramatically in illustrations and films, contributes comparatively little. The entire belt, every piece of it combined, amounts to less than 1/20% of the mass of the Earth. Now hold that figure next to what a structure intercepting starlight would actually require. Even a single uniform shell positioned at Earth's orbital distance from the Sun, just 1 millimeter thick, made of ordinary dense material, would need a mass on the order of 3 times 10 to the 23rd kilograms. In simple terms, that 1 millimeter shell, thinner than a credit card, would require roughly 125 times more material than exists in the entire asteroid belt combined. Not 125% more. 125 times more, mined, refined, and assembled, before the shell even reaches the thickness of a layer of paint. This is where the planets themselves start to look less like abundant resources and more like the only resources that could plausibly close the gap. Mercury, Venus, Earth, and Mars together carry the bulk of the rocky material remaining in the inner solar system. Disassembling all four, an undertaking with no precedent and no demonstrated technology behind it, might supply enough raw mass for a partial structure, something closer to a thin scattering of collectors than a continuous covering. But even that assumes every gram of planetary material can be converted into usable structure, an assumption that runs immediately into a second problem. The outer solar system holds far more total mass than the inner system, but almost none of it is useful. Jupiter alone contains roughly 318 times the mass of Earth, and Saturn adds nearly another 100 Earth masses on top of that. For context, the giant planets combined outweigh every other piece of the solar system, Sun excluded, by a wide margin. The catch is what they are actually made of. Jupiter and Saturn are, by mass, almost entirely hydrogen and helium, the same light gases that make up stars, not the dense metals and silicates needed to build a rigid structure. Extracting anything structurally useful from a gas giant would require transmuting those light elements into heavier ones, a process that demands the same kind of nuclear engineering used inside stars themselves. If a civilization had mastered that level of nuclear transmutation at planetary scale, building a stellar collector would likely be the least interesting use of that technology. That sleeves, when the inventory is finally totaled, is sobering. Even granting full and complete use of every planet, moon, and asteroid in the solar system, besides the gas giants, the combined mass remains a small fraction, perhaps 1/1000th, of what would be needed to fully enclose the Sun in even the thinnest imaginable continuous shell. The math does not improve with better engineering. It does not improve with more patience. There is simply not enough ordinary matter sitting in this particular solar system to build the version of the structure that most people picture when they hear the words Dyson sphere. The energy was never the limiting factor. The raw material, the actual stuff a structure would have to be made from, runs out first, and runs out by a margin too large for cleverness alone to close. And even if a civilization somehow solved the material shortage, conjuring enough matter from somewhere to physically cover even a fraction of the necessary surface area, a separate and arguably more fundamental problem would still be waiting. A continuous shell, even a thin one, even one built from material that does not exist yet, runs directly into a piece of physics that has nothing to do with how much matter you have. It runs into the question of whether such a shape could even stay where you put it. But before moving to that question, it is worth sitting a little longer with just how counterintuitive the material shortage actually is, because it inverts almost everything our intuition tells us about scale in the solar system. Stand outside on a clear night and look at the asteroid belt, or rather, look at where it would be if it were visible, that wide gap between Mars and Jupiter. Popular imagination treats it as a debris field so dense that spacecraft supposedly need to dodge through it, an image reinforced by decades of film and television. The reality is closer to the opposite. The asteroids in the belt are spread across such an enormous volume of space that the average distance between any two of them is measured in millions of kilometers. Several robotic missions have crossed the belt without making any special maneuvers to avoid a collision, simply because the odds of encountering anything at all are vanishingly small. The belt looks crowded in illustrations. In reality, it is mostly empty space, with occasional, widely separated rocks, and its total mass, spread across that entire volume, still falls short of what a single planet's moon would weigh. Consider the comparison once more, framed slightly differently. If every object in the asteroid belt were gathered into a single sphere, that sphere would be smaller than Earth's moon, with room to spare. The entire belt, source of so much science fiction imagery involving mining colonies and resource wars, would not even fill out a modest moon. This is the resource that would need to be multiplied, roughly 125 times over, just to produce a shell 1 millimeter thick at Earth's orbital distance. A shell so thin it would not stop a thrown stone, let alone shield anything living behind it from the radiation and particle bombardment of open space. The inner planets fare only somewhat better, and even there, the bookkeeping is unforgiving. Mercury, the smallest and most metal-rich of the four, contains roughly 6% of Earth's mass, almost entirely as dense rock and iron, making it in principle one of the more promising sources of raw structural material in the solar system. Venus and Mars add their own mass to the ledger, but Venus is wrapped in a thick atmosphere that would itself need to be dealt with before any disassembly could begin. And Mars, while accessible, contains barely more than 10% of Earth's mass to begin with. Disassembling all four inner planets simultaneously, an undertaking with no demonstrated technology and no historical precedent at any scale, would still leave the total well short of what a complete enclosure demands. What this means in practice is that any structure built from materials realistically available in this solar system would have to be partial by necessity, not by choice, not a shell, not even a thick swarm. A sparse scattering of independent collectors, covering a small fraction of the available surface area around the star, built from whatever inner system material could be gathered without requiring transmutation, mega-scale mining of the gas giants, or some form of construction technology that does not currently exist even as a laboratory demonstration. This is not a failure of ambition. It is an honest accounting of what is actually sitting in the box, measured against what the popular image of the structure would require. So the material limit narrows the possibilities considerably before a single support beam has been designed. But suppose, for the sake of argument, that a civilization somehow found a way around even this, perhaps by importing material from beyond the solar system, perhaps through some advanced process of matter creation that current physics does not describe. Even then, the shape most people picture when they hear the words Dyson sphere, a solid, continuous shell, runs into trouble that no quantity of material can solve. The trouble is not chemical or logistical, it is gravitational, and it was understood by Isaac Newton centuries before Dyson ever picked up a pen. There is a particular kind of disappointment that comes from solving one half of a problem only to discover the other half was never solvable in the first place. Imagine spending generations gathering material, perfecting extraction techniques on Mercury, refining metals pulled from the asteroid belt, slowly accumulating the mass needed for even a modest partial shell. Imagine reaching, after all that effort, a point where enough material has finally been assembled. The next question, the one that has been waiting patiently the entire time, is not whether you have enough material. It is whether the shape itself can exist at all once you try to put it together. And on that question, the material shortage turns out to be the easier of the two problems to face. To appreciate just how unforgiving that next problem is, it helps to remember that none of this is new territory for physics. The instability waiting on the other side of the material question was described mathematically more than 300 years before Dyson's paper. by a man working with nothing more than geometry, calculus, and an unusually persistent curiosity about how gravity actually behaves around large, hollow shapes. It is a strange kind of obstacle, one that has nothing to do with engineering skill or manufacturing capacity at all, and everything to do with a piece of mathematics that would apply just as completely to a civilization 1 billion years more advanced than our own as it does to us. Isaac Newton, working out the mathematics of gravity in the late 17th century, proved something that sounds almost too strange to be true. If you place a hollow shell around an object, and that shell is perfectly uniform, the gravitational force from that shell on anything sitting inside it, including the central object itself, adds up to exactly zero. Not nearly zero, not negligibly small, exactly zero in every direction, regardless of where inside the shell the object happens to sit. This result is known today as the shell theorem, and it has a consequence for a structure built around a star that is almost comically inconvenient. A solid shell wrapped around the sun would not be held in place by gravity at all. Gravity, the one force that keeps planets in stable orbits, that holds moons circling their worlds for billions of years without falling or drifting away, simply does not apply to a shell surrounding a central star in the way intuition expects. The star's gravity pulls on every part of the shell, certainly, but because the shell is symmetric, those pulls cancel out perfectly from the perspective of the shell as a whole. There is no net force holding the structure centered, none at all. To put this in human terms, imagine balancing a basketball perfectly still in the exact center of a hula hoop, with no string, no support, nothing touching either object. As long as the hoop and the ball stay perfectly centered, nothing moves. But the moment either one drifts even slightly off-center, by an amount too small to notice, there is nothing pulling it back. It does not return to the middle. It simply continues drifting, faster and faster in whatever direction the disturbance pushed it, because the very symmetry that created the zero-force balance in the first place is now broken. And broken symmetry in this kind of system does not self-correct. It accelerates. For a structure the size of a Dyson shell, this is not an abstract concern. Space is not a perfectly still, undisturbed environment. The gravitational pull of other planets in the solar system, the subtle push of light pressure from the star itself acting unevenly across an imperfect surface, even the gravitational influence of nearby stars over long enough timescales, all of these provide more than enough disturbance to nudge a shell away from perfect center. Once nudged, the shell does not oscillate back into balance the way a pendulum would. It drifts, and the drift compounds, because nothing in the physics is pulling it home. Left long enough, a solid shell, unsupported by anything beyond the star's own gravity, is on a one-way path toward eventually touching the star it surrounds. An outcome that ends not with a gentle collision, but with one side of an unimaginably large structure being consumed by stellar fire, while the rest of it is destroyed by the resulting catastrophe. Engineers studying the concept seriously have proposed solutions, and it is worth being fair to them because the instability is real but not necessarily fatal on its own. A shell could, in principle, be actively stabilized using some form of propulsion or station keeping, a continuous ongoing correction applied across the entire structure to counteract drift before it grows large enough to matter. The catch is the word continuous. This is not a correction applied once and then forgotten. It would need to run without interruption forever, for as long as the structure exists, because the underlying instability never goes away. The moment the correction system fails, even briefly, the drift resumes exactly where it left off, indifferent to how long it had previously been held in check. There is a second approach that avoids the shell theorem problem entirely, by abandoning the sphere shape in favor of a rotating ring or band, something closer to what is sometimes imagined as a Niven ring, after the science fiction author who popularized the concept. A spinning ring can use its own rotation to generate something resembling stability, the same basic principle that keeps a spinning top upright rather than toppling immediately. But this solution trades one problem for several others. The structural stress at the equator of a rapidly spinning ring, where the material must hold itself together against forces trying to tear it apart, exceeds the tensile strength of any known material by a wide margin, including theoretical materials like carbon nanotubes that exist only in laboratory samples, a few centimeters long, nowhere near the scale or manufacturing maturity required for a structure spanning the orbit of an entire planet. No material humanity has ever synthesized, and none currently described even in theoretical material science, comes close to having the strength required to hold a ring of that scale together against its own rotation. That's the quiet reason that almost every serious physicist who has studied the concept since Dyson's original paper has abandoned the solid shell entirely. Not because it sounds less impressive, but because it fails on terms that no advance in manufacturing or material science could plausibly fix. The instability is not a problem of insufficient strength. It is a problem of geometry itself. The same geometry Newton worked out with pen and paper, centuries before anyone imagined building anything at this scale. A structure that has no net force holding it centered, and no known material capable of surviving the alternative of spinning for stability, points toward only one remaining option if the underlying idea of capturing starlight is to survive at all. Abandon the continuous shape. Build something that does not need to be one connected piece in order to work. It is worth dwelling a little longer on why the shell theorem feels so counterintuitive, because the strangeness of it is part of what makes this entire chapter of the idea so quietly devastating. Everyday experience teaches that bigger, heavier objects pull harder, and that being surrounded by mass should mean being held more firmly in place, not less. A planet orbiting a star feels a clear, directional pull toward that star, strong enough to keep it circling for billions of years without any external correction. The instinct, carried over without thinking, is that an entire shell of material, vastly more massive than any single planet, should pull on its contents with proportionally more force, locking everything inside into a tight, stable configuration. The mathematics says the opposite, and it says so for a reason that becomes clear once you actually trace through the geometry rather than relying on intuition. Picture standing at the exact center of a hollow shell. Every patch of material on the near side of the shell pulls you toward it. Every patch of material on the far side pulls you the opposite way, toward itself. Because the shell is symmetric, every near side pull has an exact opposite on the far side, and the two cancel completely. Move slightly off-center toward one side, and something subtle but important happens. You are now closer to the nearby patches of shell material, which should, by ordinary intuition, pull harder. But there is also more shell material on the far side than on the near side, because the far side of a sphere, viewed from an off-center point, presents a larger total surface area. The two effects, stronger pull from closer material and weaker pull from a smaller surface area on the near side, balance out with mathematical precision, no matter how far off-center you move, right up until you reach the shell's own surface. The cancellation is not approximate, it is exact, a genuine mathematical curiosity that happens to be catastrophic news for anyone hoping gravity alone will keep a megastructure centered on its star. Engineers who have taken the concept seriously enough to publish on it have not simply waved this problem away. Some have proposed continuous, active correction systems, networks of thrusters or ion engines distributed across the shell's surface, constantly making small adjustments to counteract whatever tiny disturbance has begun nudging the structure off-center. In principle, this could work, in the same sense that a tightrope walker can remain upright through constant, small, continuous correction rather than perfect static balance. But a tightrope walker corrects for a few minutes at a time, with a nervous system built over millions of years of evolution. Specifically for this kind of rapid balance adjustment, a Dyson shell would need a correction system that never stops, never fails, and never falls behind. For as long as the structure is meant to exist, which on the timescales relevant to a star's own lifespan, means thousands or millions of years without a single uncorrected failure anywhere across a surface that spans the orbit of an entire planet. No engineered system humanity has ever built has run continuously, without failure, for even a fraction of that span. That spinning ring alternative deserves one more honest look, because it is the version many people picture once they learn the solid shell does not work. Often by way of science fiction, depictions of giant, ring-shaped habitats rotating slowly against the stars. The physics of rotation does provide a kind of stability that a static shell lacks. But the same rotation that provides stability also generates enormous internal stress, concentrated most severely at the structure's equator, where the material must continuously resist being flung outward by its own spin. Engineers measure this kind of stress against a material's tensile strength, the force per unit area a material can withstand before it tears. The strongest material ever measured in a laboratory, a form of carbon nanotube fiber, has a tensile strength theoretically capable of supporting structures on the scale of a space elevator reaching from Earth's surface to orbit, an achievement that itself remains entirely theoretical. Scaling that same material up to a ring spanning the diameter of a planetary orbit would require tensile strength, many orders of magnitude beyond what carbon nanotubes have ever demonstrated, even in laboratory samples too small to see without a microscope. What remains, once the continuous shell and the spinning ring have both been set aside, is the version of the idea that was there from the very beginning, quietly waiting underneath all of the science fiction embellishment. Not one connected structure at all, but many separate, individually stable pieces, each one small enough to maintain its own orbit the ordinary way. The way every planet and moon and satellite in the solar system already does, without needing a shell theorem to be defeated or a tensile strength record to be broken. This is, in fact, exactly what Dyson proposed in 1960, before science fiction ever got hold of the idea and gave it a shape he never intended. A Dyson swarm, in its simplest description, is a large number of independent objects, satellites, solar collectors, or habitats, each one orbiting the star on its own, the same way a planet or an asteroid orbits, without needing to be physically connected to anything else. There is no shell to hold together. There is no ring spinning fast enough to tear itself apart. Each individual piece obeys the same orbital mechanics that has kept every planet in the solar system circling the sun for billions of years without any active correction at all. This is the version Dyson actually described in his 1960 paper, and it solves the structural problem from the previous section almost completely, simply by refusing to be one connected object in the first place. Solving the structural problem, however, does not solve every problem, and the swarm trades the instability of a continuous shell for a different kind of difficulty, one rooted less in physics and more in sheer logistics. Consider what it would actually take to build a swarm large enough to matter. Even capturing a comparatively modest fraction of the sun's output, something in the range of 3 × 10 to the 24th watts, under 1% of the total, would still require constructing and positioning an enormous number of individual collectors, each one needing to be manufactured, launched, and placed into a stable orbit. To put this in human terms, consider that humanity has, across the entire history of spaceflight, successfully placed fewer than 20,000 functioning satellites into orbit around Earth. A meaningful Dyson swarm, even a partial one, would require a number of individual units, many orders of magnitude beyond that figure, manufactured not from material launched up from a single planet's surface, but harvested directly from asteroids, moons, and other bodies already in space. Because no chemical rocket industry could plausibly lift the necessary mass out of any planet's gravity, well in anything resembling a reasonable time frame. That's where the idea of self-replicating construction enters the conversation, and it is worth pausing on what that phrase actually requires, because it tends to get used casually, almost as a magic word that makes the scale problem disappear. A self-replicating machine, in the context relevant here, would need to mine raw material, refine it, manufacture components, assemble those components into a working collector, and also manufacture additional copies of itself, all without direct human supervision, repeated across enough generations of replication that the numbers grow from a handful of starting units into the trillions required for a meaningful swarm. No civilization, including our own, has ever built a machine capable of doing this, even at the smallest demonstrable scale. The closest analogues humanity has produced are highly specialized industrial robots that still depend on supply chains, maintenance crews, and components manufactured elsewhere by other machines and other people. A fully self-sufficient, self-replicating manufacturing system, operating autonomously across the asteroid belt for generations, remains entirely theoretical, a concept studied in engineering papers rather than demonstrated in any laboratory or factory floor anywhere on Earth. Consider, too, what happens once a swarm reaches meaningful density. Every individual collector occupies its own orbit, and orbits at similar distances from a star naturally intersect more often as the number of objects increases. On Earth, the difficulty of tracking and avoiding collisions among the mere tens of thousands of satellites and pieces of debris currently in orbit has already become a serious operational concern for space agencies, with near misses requiring active maneuvering on a regular basis. A swarm numbering in the billions or trillions, densely packed enough to intercept a meaningful fraction of a star's light, would face a collision management problem on a scale with no current precedent, where even a small percentage of objects colliding and fragmenting could quickly cascade into a debris field dense enough to threaten the rest of the swarm. A problem space engineers call a collisional cascade, already observed in miniature in Earth's increasingly crowded orbital environment. None of this means a swarm is impossible in the way a solid shell is impossible. The swarm does not violate any law of physics the way an unsupported shell or an impossibly strong spinning ring would. What the swarm requires instead is an industrial capacity, a manufacturing autonomy, and a sustained multi-generational construction effort. so far beyond anything currently demonstrated that the gap between today's spacefaring capability and a functioning Dyson swarm is not measured in better rockets or smarter engineering alone. It is measured in entire categories of technology that exist, for now, only as proposals on paper. And even granting that a civilization somehow closed that gap, built the self-replicating infrastructure, solved the collision management problem, and assembled a swarm large enough to be worth noticing, one question remains entirely separate from construction. How would anyone, anywhere else in the galaxy, ever know it was there? There is a particular kind of patience this construction effort would demand, and it is worth sitting with it directly, because the engineering numbers alone do not quite capture what is being asked. Picture, for a moment, your own relationship to a long project, something that took years rather than months, a degree, a career, raising a child into adulthood. Now imagine that same project, scaled not to a human lifetime, but to a span of construction lasting longer than every recorded human civilization combined. Carried out not by one person or one generation, but by an unbroken chain of builders, machines, and institutions, none of whom would live to see the project completed, all of them trusting that the next link in the chain would continue the work exactly as planned. This is the timescale a meaningful Dyson swarm actually demands, and it is worth returning to later once the full weight of every obstacle has been laid out. For now, simply notice that the swarm trades a problem of physics for a problem of patience. And patience, it turns out, may be the rarer resource of the two. Modeling studies of self-replicating construction, the kind published by engineers who take the concept seriously enough to run the numbers rather than wave at the idea, generally describe the process in terms of doubling periods. The time it takes for a population of construction machines to double in number by building copies of themselves. Even under highly optimistic assumptions, where each doubling period takes only a few years, the number of doublings required to go from a handful of initial machines to the trillions of units needed for a meaningful swarm runs into the dozens. 30 or more doubling periods, even at a few years each, stretches the total construction timeline into centuries. And that estimate assumes nothing goes wrong across the entire span. No interruption, no resource shortfall, no failure anywhere in a chain of replication, running for hundreds of years without pause. Consider also what density actually means for a structure meant to capture starlight rather than merely orbit near it. A handful of satellites scattered loosely around a star intercepts essentially none of its output, a fact easy to forget when picturing dramatic illustrations of glowing rings encircling a sun. To meaningfully reduce the amount of light reaching the rest of the solar system, the kind of reduction that would actually be detectable from another star system entirely, the swarm needs to achieve genuine density, with individual collectors spaced closely enough that their combined shadow becomes significant. This density requirement is precisely what reintroduces the collision risk discussed earlier, because density and collision probability rise together, and there is no way to have one without inviting more of the other. What this section has been quietly building toward is a different kind of verdict than the structural impossibility from before. The swarm is not blocked by physics. Nothing about it violates a law of nature the way the unsupported shell does. What blocks the swarm is everything else: manufacturing autonomy that has never been demonstrated, construction timescales measured in centuries rather than decades, and a collision management challenge with no working precedent at any meaningful scale. The structure is permitted. It has simply never been built by us or, as far as careful observation can tell, by anyone else either. There is a quieter implication tucked inside all of this, one that deserves to be named directly before moving on. A swarm capable of intercepting even a small fraction of a star's light would not need to be invisible by design. It would be a deliberate, visible, energy-harvesting structure, built by a civilization that wanted to use what it had captured. Its presence would not need to be hidden, because the entire purpose of building it depends on the energy being put to use somewhere by someone. This means that if such a structure existed anywhere nearby, in any of the billions of star systems within reach of current telescopes, there is a real, physical signature it would leave behind, one that does not depend on radio transmissions, deliberate communication, or any assumption about how the builders chose to announce themselves. The signature is simply heat, the same waste heat Dyson identified in 1960, radiating outward in the infrared, indifferent to whether anyone wanted it found. That signature has, in fact, been searched for, not casually and not once. Across more than 60 years since Dyson's original paper, astronomers have looked using real telescopes, real survey data, and real statistical methods for exactly the kind of infrared excess his proposal described. The most famous chapter in this search begins, somewhat unexpectedly, with data collected by the Kepler Space Telescope, a mission launched to find planets, not aliens, by watching for the tiny, regular dimming that occurs when a planet crosses in front of its star. In 2015, astronomer Tabitha Boyajian, working with a team that included volunteer citizen scientists sifting through Kepler's data as part of a project called Planet Hunters, identified a star behaving in a way no planet could explain. The star, formerly catalogued as KIC 8462852 and quickly nicknamed Tabby's star after its discoverer, dimmed irregularly, sometimes by as much as 22%, in patterns far too large and far too erratic to be caused by any planet passing in front of it. A planet produces a small, clean, repeating dip in brightness, the same shape every time it crosses its star, because the planet itself never changes size or shape. What Boyajian's team found instead was deep, asymmetric, unpredictable dimming, the kind of signal that did not match any previously catalogued astronomical phenomenon. The paper describing the discovery was, in its own careful, scientific language, honest about not having an explanation. Several natural possibilities were proposed and discussed, including swarms of orbiting comet fragments, but none fit the data perfectly. It was at this point that physicist Jason Wright, working at Penn State University, raised a possibility that made headlines around the world, though headlines, as they often do, stripped away most of the careful framing Wright himself had attached to the idea. Wright suggested that an unexplained dimming pattern was, by definition, an open question, and that among the range of possible explanations worth considering and then ruling out, a partial Dyson swarm belonged on the list, not because it was the most likely answer, but because Dyson's original 1960 logic suggested exactly this kind of irregular obscuration as one possible signature. This was offered as a serious hypothesis to be tested and likely discarded in the same spirit as any other candidate explanation, not as a triumphant announcement of alien contact. The media coverage that followed largely dropped the careful qualifications and ran instead with the phrase alien megastructure, a framing that made for excellent headlines and somewhat misrepresented the actual scientific posture being taken. Serious follow-up began almost immediately. Radio telescopes pointed at the star, listening for any signal that might accompany an advanced engineering project. Optical telescopes searched for laser pulses, another possible techno-signature. Both searches came back empty, a result that, on its own, ruled out nothing definitively, since a swarm of energy collectors has no particular reason to also be transmitting radio signals. But it did narrow the range of explanations consistent with intelligent activity. The resolution, when it came, arrived through a quieter and more technical route than any signal detection could have provided. In 2017 and 2018, researchers using ground-based observatories and data from NASA's Spitzer and Swift space telescopes measured how the star's dimming varied across different wavelengths of light. This distinction matters enormously. A solid object, whether a planet, an asteroid, or a hypothetical megastructure, blocks all wavelengths of light roughly equally as it passes in front of a star. Dust, by contrast, scatters different wavelengths differently, dimming blue and ultraviolet light more than red and infrared light, because the physics of how small particles interact with light depends on the particle's size relative to the wavelength involved. The 2017 study found exactly this pattern, more dimming in ultraviolet light than in infrared, a signature inconsistent with any solid structure and fully consistent with a cloud of orbiting dust. Lead researcher Tabitha Boyajian stated plainly that dust appeared to be the most likely explanation for the star's unusual behavior, and subsequent research building on this finding, including work proposing that the dust originated from a disintegrating exomoon or comet-like body breaking apart in orbit, has continued to refine the explanation since. What ended with this finding was not the search for Dyson spheres in general, only this one particular candidate. The broader search continued, and in some respects has only become more rigorous since. In 2024, a team led by astronomer Matthias Suazo at Uppsala University published the results of Project Hephaistos, a systematic search through approximately 5 million stars, using data from 3 major astronomical surveys: the Gaia mission, the 2-micron all-sky survey, known as 2MASS, and the Wide-Field Infrared Survey Explorer, known as WISE. The team built a filtering process specifically designed to flag stars with infrared emission too strong to be explained by their size and temperature alone, while ruling out the far more common natural explanations: ordinary debris disks, background contamination from distant galaxies, and instrument artifacts that can mimic a genuine signal. Out of 5 million candidate stars, the search returned 7. All 7 are small, dim red dwarf stars, the kind of star around which an infrared excess is least likely to be explained by ordinary astrophysics, since cool, low-mass stars do not typically host the kind of warm debris disks that produce false signals around hotter, younger stars. The research team was careful in publishing these results to call them candidates requiring further analysis, not detections. Follow-up studies have already identified likely contamination in at least one of the 7, a background radio-loud galaxy sitting close enough in the sky to the original candidate to be mistaken for part of its signal. A problem of separating a faint, distant source from another faint, distant source using instruments that, however advanced, still have limits on how finely they can resolve 2 objects sitting nearly on top of each other in the sky. In simple terms, after more than 60 years of searching, using radio telescopes, optical telescopes, infrared surveys, and now machine learning techniques applied to millions of stars at once, no confirmed Dyson sphere has ever been found. Several promising leads have surfaced, been investigated thoroughly, and resolved into ordinary, if still interesting, astrophysics. A handful of candidates remain genuinely open, neither confirmed nor ruled out, awaiting the kind of follow-up observation that takes years to schedule and complete. The absence of a confirmed detection is not, on its own, proof that no such structure exists anywhere in the galaxy. It is, at minimum, evidence that nothing of this kind exists close enough, or built brightly enough, for 60 years of increasingly sophisticated searching to have caught it yet. To put the scale of this search in human terms, consider what it actually means to screen 5 million stars for a single, specific signature. Each one of those stars produces its own light curve, its own infrared spectrum, its own particular combination of brightness across dozens of measured wavelengths. The Project Hephaistos team did not examine these by eye, one at a time, the way Boyajian's original discovery of Tabby's star unfolded through patient, manual inspection nearly a decade earlier. They built an automated pipeline incorporating a convolutional neural network, a form of machine learning originally developed for image recognition, repurposed here to separate genuine infrared excess from the confusing visual clutter of crowded star fields and overlapping background sources. Even with that automation, narrowing 5 million candidates down to 7 required multiple layers of filtering, each one designed to eliminate a different kind of false signal. Debris disks around young stars, contamination from background galaxies, instrumental noise that mimics a real measurement. The 7 that survived every filter are not 7 confirmed Dyson spheres. They are 7 stars that have, so far, resisted every mundane explanation astronomers have been able to test against them. This is worth sitting with for a moment, because it captures something true about how this kind of science actually proceeds, in contrast to how it tends to be portrayed in headlines. There was no dramatic announcement, no press conference declaring contact. There was a careful, methodical narrowing process, the same kind of process that resolved Tabby's star 9 years earlier, applied now at a scale of millions rather than 1. Whether these 7 remaining candidates eventually resolve into ordinary astrophysics, the way Tabby's star did, or whether one of them survives every round of scrutiny and becomes something genuinely unexplained, is a question that will likely take years of additional observation to answer. The kind of patient, incremental follow-up that rarely makes headlines on its own, but is the only honest way this kind of evidence ever gets resolved. There is also a deeper irony quietly embedded in this entire search, one worth naming directly. Dyson proposed in 1960 that a sufficiently advanced civilization capturing starlight would necessarily radiate detectable waste heat as an unavoidable consequence of thermodynamics. 60-some years of searching using exactly that signature have produced, so far, nothing confirmed. One honest interpretation of this result is that no nearby civilization has built anything of this kind. A second, equally honest interpretation is that building a structure capable of capturing a meaningful fraction of a star's energy output may simply be far harder and far rarer than Dyson's original optimism assumed, even for civilizations that have had billions of years longer than humanity to attempt it. Both interpretations point toward the same quiet conclusion that the rest of this story has been building toward from a different direction entirely. The barrier here was never a law of physics forbidding the structure. The barrier was always going to be everything else: the material, the manufacturing, the time, and now, apparently, the simple absence of anyone who has managed to put all of those pieces together, even once, anywhere within reach of 60 years of careful, patient looking. That word, time, deserves one final dedicated pass of its own, because everything covered so far, the energy, the material, the structural physics, the manufacturing, the detection effort, has circled the same unstated assumption without ever naming it directly. Every solution proposed for every problem in this story assumes a civilization with enough patience and enough institutional continuity to see a centuries-long project through to completion. That assumption, it turns out, may be the largest one of all. Return for a moment to the doubling periods mentioned earlier, the modeled construction timeline in which a population of self-replicating machines grows from a handful of starting units into the trillions needed for a meaningful swarm. Even under generous assumptions, this process requires somewhere in the range of 30 or more doublings, and even at only a few years per doubling, the total span stretches into centuries. Centuries on their own do not sound impossible. Human civilization has built things that lasted centuries before. The deeper question is not whether centuries can pass. It is whether any institution, any government, any continuous chain of authority and purpose has ever actually survived that long without interruption, without losing the thread of the original project somewhere along the way. Consider the longest continuously maintained engineering projects in recorded human history. The construction of medieval cathedrals across Europe often spanned generations, with the architects who laid the foundation knowing they would never see the completed structure, trusting that their successors would carry the work forward according to the original design. Cologne Cathedral, begun in 1248, was not completed until 1880, a gap of more than 600 years, with long stretches in the middle where construction halted entirely for lack of funding or political will, only resuming centuries later under entirely different builders working from surviving plans. This stands as one of the most extreme examples of sustained human construction effort, and even it required multiple complete interruptions, periods spanning decades where nothing was built at all, before the project eventually reached completion under conditions its original architects could never have anticipated. A Dyson swarm construction effort cannot tolerate that kind of interruption in the same way. A cathedral, paused for 2 centuries, simply sits unfinished, stone and mortar, weathering slowly but not actively degrading the project's eventual completion. A self-replicating construction system, paused for even a few decades, faces a different problem entirely. Machines designed to manufacture other machines require maintenance, software updates, and ongoing technical oversight. A construction effort that goes unsupervised for an extended period risks losing track of its own replicating population, accumulating errors across generations of self-copying that, left uncorrected, could compound into systems that no longer function as designed. A problem closely related to the kind of generational data degradation engineers worry about in any system that copies itself repeatedly without external correction. No government in recorded history has maintained a single continuous policy, uninterrupted by revolution, regime change, war, or simple shifting priorities, for anything approaching the centuries this project would require. The Roman Empire, often cited as one of history's longest-lasting political structures, endured for roughly 500 years in its Western form. And even that span included civil wars, changes in fundamental governing structure, and long periods of internal instability that would have devastated any technical project requiring continuous, coordinated oversight. Modern nation-states, by comparison, are younger still, and the technological infrastructure underlying any sufficiently advanced civilization's construction effort would itself need replacement, upgrading, and maintenance across that same span by institutions whose own survival across centuries cannot be assumed. To put this in human terms, consider that the entire history of powered flight, from the Wright brothers in 1903 to landing astronauts on the moon in 1969, spans less than 70 years, a single human lifetime. The entire span of recorded human civilization, from the earliest cities and written language to this very moment, covers roughly 5,000 years. A construction project requiring multiple centuries of uninterrupted institutional commitment is not simply longer than any project humanity has completed. It is long enough that the civilization undertaking it would need to survive, intact and purposeful, across a span comparable to a meaningful fraction of all of recorded history, without the kind of political upheaval, economic collapse, or simple loss of interest that has characterized every human civilization that has ever existed. This is, in the end, the quietest and perhaps the most decisive obstacle of all. Not a law of physics, not a shortage of raw material, though that shortage is real. Not even the absence of self-replicating manufacturing technology, though that absence is also real. The deepest obstacle is institutional patience, sustained without interruption across a time scale longer than any human institution has ever managed, by a civilization that would need to remain unified in purpose for longer than empires have lasted, in service of a project whose payoff would not arrive until long after everyone who began it was gone. Consider what this would actually feel like, from the inside, for the people living through it. The generation that begins the project understands its purpose clearly, having designed it, debated it, and chosen to commit resources toward it. Their children, born into a civilization already partway through construction, inherit the project rather than choosing it, the same way every generation inherits the unfinished work of the one before. By the time 10 or 15 generations have passed, a span of perhaps 300 or 400 years, even using generous estimates of generational length, the original motivations behind the project exist only in historical record. Study the way modern engineers might study the reasoning behind an ancient irrigation system, with respect but without the lived urgency that drove its original builders. Maintaining commitment to a project under those conditions requires not just technical continuity, but cultural continuity. A civilization that successfully transmits not only the knowledge of how to continue building, but the conviction that continuing is worthwhile across a chain of generations long enough that no single person along that chain will ever personally benefit from the structure's completion. History offers little encouragement on this front. Religious institutions, some of the longest continuously operating organizations humanity has produced, have maintained core practices across centuries, even millennia. But they have also split, reformed, and redirected their efforts repeatedly across that same span, rarely maintaining a single unbroken technical objective the way an engineering project would require. Scientific institutions, comparatively young by this standard, have existed in their modern form for at most a few centuries. With funding priorities, research directions, and institutional structures shifting dramatically across even single human lifetimes, let alone across the centuries a swarm construction effort would demand. There is, quite simply, no existing model of an institution anywhere in recorded human history that has maintained a single coordinated technical project, uninterrupted, across a timescale long enough to be relevant here. None of this proves the project is permanently impossible for any civilization anywhere. It is entirely possible that a sufficiently advanced society, perhaps one that has solved problems of governance, succession, and institutional memory that remain unsolved on Earth, could sustain a project across the necessary centuries without losing coherence. It is equally possible that the very challenges of governance and succession that plague human institutions are universal features of any society, complex enough to attempt a project this large, in which case the absence of any confirmed Dyson sphere anywhere in 60 years of careful searching may reflect something more fundamental than bad luck or insufficient looking. It may reflect a genuine galaxy-wide difficulty in sustaining the kind of unbroken institutional patience that a project at this scale actually requires. A difficulty that may apply with equal force to any civilization, anywhere, regardless of how advanced its physics or its engineering eventually becomes. Step back now and look at everything gathered so far, set down side by side. The energy is there, abundant beyond any planetary need, arriving every second, regardless of whether anyone is ready to use it. The raw material in this particular solar system falls short by orders of magnitude, even before any structure is designed. The solid shell that fiction prefers cannot hold itself together. Undone by a piece of geometry Newton worked out centuries ago, the swarm that physics permits demands a manufacturing capability, a construction timeline, and an unbroken institutional patience that no civilization, including whatever built ones we might eventually find, has yet demonstrated anywhere within reach of careful observation. Each obstacle, taken alone, sounds like a problem awaiting a clever solution. Taken together, across energy, material, structure, manufacturing, and time, they describe something closer to a filter, one that any civilization attempting this particular project would need to pass through completely, with no partial credit for solving 4 obstacles out of 5. And underneath all of this, quietly, sits a question that has nothing to do with engineering at all. It is worth remembering, here, near the end of all this arithmetic, what Dyson actually believed he was doing when he wrote that single page in 1960. He was not drawing blueprints. He was not promising anyone, including himself, that the structure was buildable within any particular span of time, or by any particular civilization, including a future version of our own. He was reasoning quietly about where growth leads, if growth is allowed to continue uninterrupted for long enough. And he was offering astronomers a place to look, a signature to search for, in case somewhere among the billions of stars scattered across this galaxy, some civilization had already crossed the threshold he was describing. He was, in the most literal sense, proposing a search, not an engineering plan. Everything that came afterward, the popular image of a solid, gleaming ball, the assumption that this was a near-future human possibility, the disappointment some people feel on learning it has never been built. None of that came from Dyson himself. It came from everyone who took his quiet, careful speculation and dressed it up as something more certain than he ever claimed it to be. You have spent the better part of an hour now sitting with a structure that does not exist, tracing through energy outputs and asteroid masses and gravitational instabilities that were never going to add up to a finished blueprint by the end of this. That was never really the point. The point, if there is one, is something closer to a mirror, held up at a useful distance. Your own civilization is, by any honest measure, still extraordinarily young. The technologies you rely on every day, electricity, computing, spaceflight itself, are each barely more than a century old, younger in some cases than your own grandparents. The sun has been burning steadily, producing that same staggering output for 4.5 billion years already, and will likely continue doing so for several billion more. Against that backdrop, the absence of a finished Dyson swarm around your own star says almost nothing about what is possible. It says only that a civilization barely a century into harnessing electricity has not yet attempted a project that, by its own honest calculations, would require centuries simply to begin showing meaningful results. There is a kind of comfort hiding inside that thought, even if it does not announce itself as comfort right away. The absence of evidence, 60 years of careful searching turning up nothing confirmed, does not have to mean the idea was wrong. It may simply mean that everyone, everywhere, capable of attempting this kind of project is still early. Early in the same sense, a single cell is early relative to a forest, or a single brick is early relative to a cathedral that will not be finished for 600 years. Dyson was not describing something humanity had failed to achieve. He was describing a horizon, a place civilizations might eventually arrive if they survive long enough, sustain enough patience, and never lose the thread connecting one generation's effort to the next. The stars above you tonight, every one of them, are still doing exactly what they have always done, releasing their light in every direction without restraint, without any structure built to catch it, without anyone, anywhere within reach of 60 years of careful listening, having claimed even a fraction of what is being given away for free. That is not failure. It is simply where things currently stand, in a universe old enough to have produced stars and planets, and at least one species curious enough to do the arithmetic, but perhaps not yet old enough, anywhere, for that arithmetic to have been finished. There is something quietly steadying in realizing how much of this story was never really about aliens at all. The 7 candidates flagged by Project Hephaestus, the dust cloud that turned out to explain Tabby's star, the careful, decades-long search for an infrared signature that has not yet confirmed anything. All of it functions less like a hunt for someone else out there, and more like a slow, patient mapping of the boundary between what physics permits and what any civilization, anywhere, has actually managed to do with the time it has been given. The boundary keeps turning out to be further away than the popular imagination expects, not because nature is withholding some secret, but because the gap between permission and achievement, the same gap that runs through almost every chapter of how civilizations interact with scale, simply takes longer to close than impatience would prefer. Think for a moment about your own pace through an ordinary day, the small, incremental tasks that accumulate into something larger only when looked back upon from a distance. A single afternoon rarely feels like progress toward anything vast. A single year in isolation can feel almost stationary, the kind of stretch where nothing seems to have moved. It is only across years, strung together without interruption, that anything resembling a finished project begins to take shape. Civilizations work the same way, only slower, and the projects worth measuring against a civilization's full lifespan are not the ones that finish in a single generation. They are the ones, like a cathedral begun by builders who never saw its completion, that ask one generation to trust the next, indefinitely, without any guarantee the trust will be honored. Perhaps that is the quietest lesson sitting underneath everything covered tonight. Dyson's structure was never really a test of physics. Physics, as it turns out, permits the swarm and forbids only the version fiction preferred. The real test, the one still unresolved after 60 years of careful searching across millions of stars, is a test of patience, stretched across timescales no civilization has yet proven it can sustain without breaking. Somewhere among the billions of stars in this galaxy, that test may already be underway, quietly, in a system too distant and too dim for any telescope humanity currently possesses to notice. Or it may be that no one, anywhere, has gotten far enough yet to even begin. There is no way tonight to know which of those two possibilities is true. That uncertainty is not a gap waiting to be filled with disappointment. It is simply the honest shape of where the search currently stands, 60 years in, with 5 million stars screened and 7 candidates still open, and a single star nearby, your own, still pouring its light outward into the dark, unclaimed, exactly as it always has. You can walk outside tonight, if the sky happens to be clear where you are, and look up at almost any star and know that what you are seeing is, in every case, so far examined, exactly what it appears to be. An ordinary star, unenclosed, unharvested, spending its light into empty space the same way it has for billions of years, with no swarm of collectors waiting in its orbit, no shell wrapped quietly around it, nothing built by anyone to catch what is otherwise simply given away. That was never the terrifying part, and it was never really the disappointing part either. The structure violates no law of physics. Nothing about a Dyson swarm is forbidden by nature the way faster-than-light travel or a perpetual motion machine would be forbidden. It has simply never been built. Not by us, not yet, and not, as far as 60 years of patient searching can currently tell, by anyone else within reach of our instruments. Unbuilt is not the same word as impossible. The difference between those two words is where this entire story has been quietly living the whole time. There is something almost gentle in landing on that distinction rather than a harder one. A civilization does not need to have failed at something in order to simply not have reached it yet. You have not failed at anything by living in a century that has barely begun to use electricity, by any cosmic measure, let alone capture the output of an entire star. You are early. Your whole species is early, standing at the very beginning of a timeline that, if it continues uninterrupted for long enough, leads somewhere Dyson sketched out on a single page in 1960 and never claimed to have finished himself. Picture, if you want a single image to carry out of all of this, a single star, somewhere among the 100 billion or so scattered across this galaxy, still burning exactly as it has for ages, its light pouring outward in every direction. Most of it never touched by anything, never gathered, never used, simply continuing on into the dark until it fades into the background glow of a universe that has more light in it than anyone, anywhere, has yet found a way to keep. Somewhere among all those stars, a civilization older than ours, more patient than ours, may already be decades or centuries into a project like this one, quietly, without fanfare, the way any project this slow has to be carried out. Or perhaps no one has. Perhaps the light simply keeps leaving, unclaimed, everywhere, all the time, because patience at this scale is rarer even than the matter required to build with. Maybe somewhere out past the reach of every telescope we currently have, someone has already begun. Maybe no one has. Either way, the light keeps arriving, unclaimed, patient, in no particular hurry to be caught. Maybe somewhere out past the reach of every telescope we currently have, someone has already begun. Maybe no one has. Either way, the light keeps arriving, unclaimed, patient, in no particular hurry to be caught.